In this video we'll take a look at how DTA can be used to create alloy phase diagrams. So here's a phase diagram for a eutectic alloy, and this is an example for silver and copper mixtures that create an alloy, and this diagram's been adapted from the reference shown here, and just to note that the values and the lines here are just approximate, but it's to illustrate a point. So first thing to say is that over here we've got the atomic percent copper, so when we're at this point we've got 100% copper, and over on this other side we've got 100% silver. So when there's 0% copper, it's 100% silver. Okay, and up here we've got liquid, so everywhere in this zone is all liquid, and then in this zone here we've got a solid referred to as alpha. So this is a particular phase. So alpha is a solid solution of silver with a small amount of copper dissolved into it. We then have another zone here which is liquid plus solid alpha, and then we have another zone which is solid beta. So in this zone, this area here, anywhere here with this composition and this temperature will be a solid phase referred to as beta. And beta again is a solid solution, but this time it's a solid solution of copper with a small amount of silver dissolved into it. And the reason that they're called alpha and beta is just that by convention the component over on the left hand side, so this being 100% silver, just is chosen by us, but because this is over on the left hand side it's referred to as alpha, and because this is over on the right hand side this phase is referred to as beta. Okay, then in this zone here we have a liquid plus beta, which is a solid solution of copper with a small amount of silver dissolved into it, and the liquid of course in all of these examples is a mixture of liquid silver and liquid copper. Okay, so let's continue then. Down here we have a solid which is a combination of the alpha solid solution and the beta solid solution. So it's a combination of phases there in this whole region here, which is all solid. Okay, a few things to point out in addition is that here this point is the melting point of silver, this point here is the melting point of copper, and then we've got this blue line referred to as solidus, and this is the line below which only solid material is present. So if we look at this blue line, anywhere below this we only have solid material. And then we also have this red line which is referred to as liquidus, and this is the line above which only liquid is present. So this red line, anything above this we only have liquid. Finally we have solvus, the solvus line, and this is the solubility limit for the solid solution. And below this the single phase breaks up into two phases. So let's imagine we're somewhere here and we've got this alpha phase. If we cool that down, it then splits into two separate phases, the alpha and the beta. So it's the solubility limit for this solid solution. Okay, and another thing to mention is the eutectic point, and this is the lowest point at which we get the transition from liquid to solid as we cool down, and it goes straight from a liquid to a solid. And you'll notice that this is lower than the melting points of the pure components. And so this eutectic point is referred to, if we have the composition at this point around 40%, 40 atom percent copper, this is referred to as a eutectic mixture. So let's now imagine that we've got 70% by atom ratio, and we're at 1100 degrees. If we had a mixture there and we cooled it down in our DTA, we would pass through these different phases and we could get a thermogram, and let's see what that would look like. So it would look something like this, and this point here would be the point at which we start to get some solid material, so that is T liquidus, so that helps us find out where the liquidus point is, and then we also have T solidus, so when it's all becomes solid. So we can use DTA to start to build up these phase diagrams, and we could repeat this process for different compositions and build up the phase diagram. Okay, so just to mention another example, this is silver silicon, and so we've got the eutectic point, we've got the melting point of pure silver, pure silicon, we've got the solidus, we've got the liquidus line, and what's interesting is that the solubility of silver in solid silicon is negligible, so we get no alpha phase. So over in this region here we get no alpha phase because of this insolubility of silver into silicon. So we just have liquid, which is a mixture of silver and silicon liquid, and then we also have solid silicon. And also the solubility of silicon in solid silver is negligible, so we have no beta phase. So again, in this region we have a liquid, which is liquid silver and liquid silicon plus silver solid. And then down here we have two separate phases forming the solid in this region. So all of this is solid, and it's a combination of silver solid and silicon solid. So there'll be sort of small grains and grain boundaries between these to form the alloy. Okay, so that is another example of a eutectic alloy phase diagram. And so that has been a video about the use of DTA to examine alloy phase diagrams. I hope you found that useful. Please remember to like, comment and subscribe, and thanks very much for watching.